Whenever we need to perform high-level sequential control of a machine or process, we have the option of creating the logic in the sequential function chart, or SFC, programming language. In the example presented here, we have a rotary knife machine with two sections, an in-feed and the knife itself. So, looking to the existing logic, we find a program for each section. Opening the logic for the in-feed, we find some very simple simulation logic. Upon the first scan of the controller, the section status is set to stopped. This stopped bit is an output parameter that may be connected to the high-level control logic. On rung 1, we have a start input parameter that triggers a timer. This timer simulates the time it would take for the in-feed logic to get the in-feed running. The start command also unlatches the stopped status. Upon completion of the timer, the status is set to running. Again, this is an output parameter that will let the high-level control know when the section is in the running state. On rung 2, we have similar logic, but this time for stopping the in-feed. Closing this routine and opening the logic within the knife program, we find that we have exactly the same simulation logic. Let's move to the main program and create an SFC routine that will control both of the machine sections. Of course, to make this an SFC routine, we select Sequential Function Chart from the Type dropdown. Now we need to add a JSR to the main routine so that our new subroutine will be executed by the controller. Opening our SFC routine, we see that we are automatically provided with a first step and transition pair. Steps and transitions include backing tags that are named by incrementing the numerical value in the name. By default, these tag structures are created at the program scope of data types specific to the instruction type. Expanding them, we can see the extensive data available to the programmer. Note that we can also rename these tags. So, for example, let's make this first step our stopped step and indicate that in the tag name. Back within the logic editor, we see that the name has indeed been changed. Steps can have actions programmed into them. However, we will program the stopped actions later. For now, let's turn our attention to the transition. We want the machine to transition from the stopped state into the starting state when a hardware push button is pressed by the operator. So we enter start into the transition. Creating the start tag, let's make it an input program parameter. Of course, transitions are looking for a Boolean result, so we make this tag a bool. Because we have made this an input parameter, we can connect it to hardware tags later when the hardware has been installed and we have added it to our I/O configuration. For testing, we will simply toggle this bit manually. Now we can add the starting step. In the starting step, we need to command the two sections to start. So let's add an action into which we can program structured text logic. We'll create this command as an output parameter connected to the input parameter in the in-feed program. Although we could program the second command within the same action as the first, let's see how we can add a second action. Again, we create the command as an output program parameter connected to the input parameter in the relevant program. Because we have programmed these commands into separate actions, we have the ability to access the step properties and change the order in which the actions execute. For this step, we want the ability to transition to the running step if both sections report back that they are running. However, if the two sections do not report back as running within a reasonable time, we want the machine to abort. So we will add a selection branch diverge instead of a single transition. Transitions do require a Boolean condition. However, these conditions do not have to be a single bit. We can also employ Boolean statements. So in this example, we use an AND statement that requires both sections to report back as running before the transition can occur. Now we create these conditions as input parameters connected to the relevant status output parameters in the two sections. For the other transition, we want the machine to abort if the two machine sections have not reported back as running within 5 seconds. As it so happens, step instructions include built-in timers that begin running when the step starts and stop running when a transition occurs. We can set the preset for the timer to 5,000 milliseconds, and if the step doesn't transition before then, the done bit will turn on. Then we simply use that done bit as the condition for the second transition. We will program the aborting branch later. For now, let's continue down the main branch by adding the running step. Let's add an action that we can use to clear the start commands. In this example, we program all of the logic into the single action. For the transition out of the running state, we use the stop command as our condition. As with the start command, we create the stop command as an input parameter that we can connect to hardware at a later time. The stopping step follows the stop command transition. For the actions, we will again create two actions, one each for the stop commands to the two sections. Of course, these new commands are created as output parameters connected to the inputs in the two section programs. As with the starting step, we want the stopping step to abort the machine if the sections do not report back as stopped within 5 seconds. So we add a selection branch diverge. This time, the first transition occurs only when both sections have reported back as stopped. Again, the second transition occurs if the step timer done bit turns on. Recall that our first step is the stopped state, so we need to loop this first transition back up to the top. Now that our main sequence of logic is programmed, we can move on to programming the aborting sequence. So we begin with the aborting step. In this case, we need for the action to clear the start and stop commands, set the stop bits, and clear the run bits. For the transition, we would like to proceed straight through to the aborted state regardless of conditions. To do this, we simply write a constant of 1 into the transition condition. Because we are leaving the stop bits latched, no actions are required in the aborted state. To transition out of the aborted state, we require a reset input from the operator. Again, because the stop commands have already been issued, we require no action on the part of the resetting step. Since it is possible that the reset fails, we will add another selection branch to Verge. If both sections report back as stopped within 5 seconds, we will transition to the stopped state. If they do not do so, we will transition back to the aborting state. Now we need to connect the 3 aborting transitions to the input of the aborting step. Note that we may readily attach 2 transitions directly to the input of a step. However, the third cannot be connected directly to the step. We can, instead, connect it to the output of one of the other 2 transitions, and it will lead to the aborting step as desired. Now we see that our connecting lines have become quite confusing. To solve this, we can hide these 3 line connectors, and they will be replaced with references. With the connectors hidden, we move the branch above the aborting step to complete our cleanup. Notice that the references include hot links that take us directly to the other end of the reference. Now we connect our final transition to the stopped state. Again, we can do some cleanup. Getting back to our stopped state, let's add an action wherein we can clear our commands. Let's check for errors. Now we can save and download to the controller for testing. Let's create a watch window that will allow us to toggle the command bits and view the results. Writing 1 to the start command, we see the start commands to the sections turn on. Then, in 2 seconds, the sections report back as running, and the sequence moves to the running state and clears the commands. Writing 1 to the stop command, the stop commands are sent to the sections, which report back as stopped in about 2 seconds, resulting in a transition to the stopped state. Let's increase one of the timers in the section logic to test our aborting sequence. Commanding a start, we see that only one of the sections reports back as started in time, so the sequence transitions to the aborting step and the sections are commanded to stop. If we reset now, we will be successful. However, once we try to start, we abort again because we have not repaired the original problem. So, going back and fixing the problem, we see that the sequence returns to normal operation.